Hello students, welcome to the class. So today we will see the NCERT exercise of chapter 3 classification of elements and periodicity in properties. Disclaimer given here. In today's session we will be covering the questions of NCERT exercise. So there are 40 questions in total given in your NCERT exercise. So I have picked up some important questions. So that totals to 11. You can see the index of those given in the last row. Here is your first question, NCERT exercise 3.5. On the basis of quantum number, justify that sixth period of the periodic table should have 32 elements. So how you would justify it? So you have some time to solve this question. Your time starts now. Just think of how the period helps in determining the quantum number and how they are related to each other. Okay. So your time is up. We know that the 6th and 7th period have 32 elements. But how do we know it? So let us go step by step to understand this. What is the first step? The first step is that we know that there are 32 elements in the 6th period. Now when we say 6th period, what do we know? We know that what is the maximum principal quantum number that is possible. But before that, if you know that how many electrons are filled in that period, then you will know that what is the number of elements. So if I am saying 6th period, then n is equals to 6. Okay. So this is for sure that the maximum principal quantum number allowed or the outermost principal quantum number is 6. Now what are the orbitals or subshells that we will fill in n is equals to 6? To do that, we know that we will start from 6s. Okay, so we will have 6s. Then after that, if you know the rule, n plus l rule, you can write the further energy subshells. So 6s, then 4f, then 5d, 6p. As soon as you see the 7s, you won't move forward. Okay, you will stop here because 7s will be filled in the 7th period. So what are the subshells that will be filled in the 6th period? So those are starting from the 6s. Remember, if you are talking about the 6, just take the s subshells. As simple as that. Then 6s, then 4f, 5d, 6p, and as soon as you see the next highest quantum number, then stop there and include the green part here. Okay, so 6s, 4f and 5d and 6p in your calculation. Now what I would say, I would just try to calculate the number of electrons in each of these subshells. So the 6s has 2 electrons, 4f has 14 because f has 7 orbitals, so 7 to the 14. 5d has 10 electrons and 6p has 6 electrons. Now what is the total? The total goes to 32 electrons. Therefore, in the 6th period, 32 electrons are to be filled. Now, that corresponds to the total number of elements. And hence, each electron corresponds to one element. Therefore, 32 elements are in the 6th period. So, in this way, you will try to calculate the number of elements in a given period. Very simple. Just take that number. So say we are talking about the 6th period, we'll take 6, start from the 6s, the smallest subshell possible for the 6, and move on according to the above principle. Now wherever you see the next highest principal quantum number, stop there, and all the subshells that you got, try to fill the electrons in them, and the number of electrons will be equal to the number of elements. So this gives your total number of elements in a given period. I hope you're getting the point here. Now moving on to the next question. In terms of the period and groups, where you would locate the element with z is equals to 114. So just try to solve it logically, right? So I will also give you a logical, systematic way to solve it. Before that, you have some time. Just try by yourself if you can see that which is the period and group in this 114th element. Your time starts now. Okay, so you have 5 more seconds. So your time is up. Let us look what is the correct answer. So the correct answer will be period will be 7 and group will be 14. Okay, so those who have solved it for this two numbers, very good. Now if you have not solved it, let us see the logical steps that are involved in solving it. So first of all, what you will do, you should know that period corresponds to the highest principal quantum number. Now with this systematic way, you can know the period and group for any atomic number. So this is important to note down. First of all, we will move to the period determination. Now to identify that, we will look for the elements that are present in each period. So for the first period, 2 elements are possible. Okay, so Z is equals to 2 is maximum possible for the first period. Then we will move on to the second period. So in second period, 8 elements are possible. So 2 plus 8, that gives you 10 elements. Then in the period third, again 8 elements are possible. So 10 plus 8, 18. Now what about the fourth period? How many elements are possible in the fourth period? So that will go up to 18. Okay, so 2, 8, 8, 18. So just add 18 plus 18, that will give you your atomic number possible up to group 5, group 4. Again add 18 to this 36, that will give you 54. Moving on to the group 6. So first is 2, then 8, 8, 18, 18, then 32. So 54 plus 32 means up till 86 atomic number is possible till the group 6. What is the last period? It is group number 7. As soon as you move to the group 7, you will encounter the atomic number which is greater than the 114, which is 118. So there are 118 elements in the group, in the period 7. So therefore, you will take them in the group in the period 7. See, it is written here. Since Z is equals to 14 is greater than 86, the element is in the period 7. So simply you have to add the elements in each period, and as soon as you cross the given number, which is 114, you will place it in that group. So if you calculate it for the period number 7, you will get it for 118 elements which is greater than 114. Therefore, it will lie in the 7th period. So I guess this is clear to you. Now let us move to the group determination. How you will identify the group? I guess it is very simple. You just have to know the outer electronic configuration. So outer electronic configuration after radon is 28 electrons. So there are 86 electrons up to the radon. We know it because the atomic number of radon is 86. We have seen it. We have calculated that part. Now 86 are been filled. What are we left with? We are left with the 28 electrons. So 114 minus 86, that gives you your 28 electrons. Now you have to fill this 28 electrons in the next higher shell. Again, that same logic we have applied in the previous question. Since we are considering the 7th period, therefore we will fill the S subshell of the 7th period first. So that gives you 7s2. So now 88 electrons are being filled. Moving on to the next one, it is F, 5F and FS14. So 88 plus 14, 102 electrons. Now you are moving in the 7th period one by one. So we have reached up to 102 atomic number. Then after 5f comes your 6d. So that contains 10 electrons. That totals up to 112 electrons. And lastly, in the 7p, we will place the remaining 2 electrons that counts up to the 114 number. So in this way, you will fill the electron. Now, it may be possible that you must be finding difficulty in identifying that which subshell will come after the 7s, which will come after the 5f. So I will request you to just practice this thing by yourself. We have seen this thing of writing the subshell in energy order in the structure of atom. So you must practice that part. Now, since your last electron is going to the p subshell, that means your element belongs to the p block. So that thing is for sure that your element belongs to the p block. Now, how you would identify the group number? Now, this process is different for different blocks. Here we are interested in the p block. So the simple method is just add the valence electrons of s and p with 10, and that will give you your group number. So there are 2 electrons in the valence s subshell and 2 electrons in the valence p subshell. So 10 plus 2 plus 2, which gives you your 14. Therefore your group will be 14. Now this thing is true for the p block. No question in that. What you do? You just count the number of electrons present in the valence subshell for s and p and add it with the 10. Now what is the method for other block? For s block, whatever be the number of electrons present in the outermost s subshell gives you your group number. Like if you take the example of sodium, it has S1, therefore it belongs to the group 1. You take the example of magnesium, the outermost configuration is S2, so it belongs to the group 2. So you just have to count the number of valence s electrons, as simple as that. Now in case of D block, there is a common method, but you must be aware about the exceptions like your chromium and copper. In general, what we do? We count the number of electrons present in n-1d and ns, and then that gives you your group number. For group 3, it is very easy in case of F block. Why? Because every element of the F block belongs to the group 3. So this is very, very important, that every element of the F block belongs to the group 3. So in this way, you will determine the group number for every given atomic number. I guess this process is clear to you. It's quite simple to do, and it is beneficial for each and every atomic number. Now moving on to the next question. Consider the following species. So 6 species are given here, all are ions, and you have to look that what is common in all of them. Second thing, you have to understand that how you will arrange them in the order of increasing ionic radii. So your time to solve this question starts now. So there is a common name for each of these elements, and you can arrange them in the order of increasing ionic radii. I have given you a small shortcut for that. So let us look at the correct answer. First of all, let us see that what is common in them. Yes, that is that they are isoelectronic species. So that is for sure. What are isoelectronic species? The species with the same number of electrons are called as the isoelectronic species. Now what is the number of electrons in each of these elements? Or I would say species. So there is a very simple method to calculate that. Just take the atomic number of the given element. If the charge is negative, add the number to that. If it is positive, subtract that number. How? Let us see. Suppose we are considering for nitrogen. So the atomic number is 7 and the charge is negative. So we will add that number. 7 plus 3, 10 electrons. Similarly for oxygen, 2 negative charge is there. Atomic number is 8. Since the charge is negative, we will add 2 electrons. What about fluorine? F minus, again the charge is negative and the atomic number is 9, so 9 plus 1 gives you 10 electrons. Now moving on to the next cationic species, which is sodium plus. Now sodium plus, since the charge is positive, we will subtract 1 from it. Okay, 1 positive charge, so we will subtract 1 from it. So 11 minus 1, 10. For magnesium 2 plus, we will subtract 2 from the 12, which is the atomic number of magnesium 2 plus. And lastly, for the aluminium, we will subtract 3 from 13. So what you can see in all of this, you can see that they all have the same number of electrons. Therefore, all of these are ionic species. Now, the question arises, how you would arrange the isoelectronic species in the increasing order of ionic radii. So, how we will do it? Let us see. So, there is a very quick formula to do so. What does it say? That your ionic radius is inversely proportional to the integral value of the charge. Or you can also say it is what? It is directly proportional to the it is inversely proportional to the positive value and directly proportional to the negative value. Let us see how it is possible. So this you can get it with the help of the question that we have got. If I arrange all of these species in the increasing order of nuclear charge, then the N3 negative will be in the back side because it has the least value of integer, 3 negative. Okay, and aluminium, it is 3 positive, which is the largest integral number in all of this. Now I have arranged all of this in the increasing order of charge. You can see it very clearly, and remember I have taken the integral value. Now this integral value and ionic radius are inversely proportional. Therefore, the order of ionic radii will be Al3 plus, Mg2 plus, Na plus, F, O2 minus and N3 minus. Okay, you can also say that it is a order of ionic radii. I guess this part is clear to all of you. So you must remember this boxed formula always for your reference, that how do you compare the isoelectronic species. The click part is that your ionic radii is inversely proportional to the integral value of charge. Moving on to the next question. Explain why cation are smaller than anions are smaller and anions are larger in radii than their parent atom. So you have to compare with their parent atom. Your time to solve this question starts now. So what is the reason behind it? Five more seconds. Okay, your time is up. So two things are there. We will discuss them one by one. First of all, let us talk about the cation. So it is always true that your cation will be smaller than the parent atom. What is the reason behind it? Because as you remove one electron, now the same number of protons are there in the nucleus, but the number of electrons has gone down. As a result, the effective nuclear charge on that outer electrons will increase, and that will result in a smaller radii. So this can be understood in the terms of sodium. See, we have removed one electron. Initially it has 11 electrons, now it has 10 electrons. Since the number of proton is same, means the number of protons that are applying the force are same, but the number of electrons on which the force is applied has been reduced. As a result, the effective nuclear charge has increased for each and every electron, and hence the size has contracted. Okay. So in case of sodium, it goes from 186 picometer to 95 picometer. So you can see how drastically this has happened. Now similarly, we will consider for the anionic part. Now what happens in case of anion? So we'll try to understand it one by one. First point is that the size of anion is larger than parent atom. So this is given in the question, and this is a important point to remember. Now why it is happening? So in this case, your number of protons is same, okay, but the number of electrons is greater than the number of protons, and that is the reason it is acquiring a negative charge. Now what will be the outcome of this? The outcome of this will be that there will be repulsion, means they will repel each other. The electrons will repel each other and they will move further. Ionization energy. So you have to calculate the ionization energy, but the unit is important here. You have to calculate in terms of joule per mole. Okay. So your time to solve this question starts now. Okay, your time is up. Let us see how we can solve it. So the first part which you should remember is that what is the relation between the ionization energy and the ground state energy of a hydrogen atom. So energy of an electron in the ground state is equals to the negative of the ionization energy per atom. So just try to understand this in a much more physical way. So your proton is attracting the electron, and as a result it is having an energy of minus 2.18 into 10 to the power minus 18. So since this energy is negative, that means your electron is stabilized by this much amount of energy. Now to remove the electron, you have to apply the opposite force. Therefore you have to apply the opposite energy, and hence we have put a negative sign. Okay, so to remove an electron from the ground state of the hydrogen atom, you have to apply this same amount of energy. But remember students, that this is for one electron and you have to calculate for 1 mole, because the unit should be in joule per mole. I guess this part is clear. If this is clear, then we can move on to the answer. So first, energy of electron in the ground state. So meanwhile you can try to calculate it for per mole if you want. It's very simple if you know it for the 1 electron. So the energy of the ground state electron will be 2.18 into 10 to the power minus 18 joule. So this is the ground state energy already given in the question. Now what will be the energy that will be required to pull off that electron? It will be plus 2.18 into 10 to the power minus 18 joule. So this is for 1 electron. Now what will be the case for 1 joule? It's very simple. 1 mole, it will be very simple. Just multiply the 1 electron term with the Avogadro number. So to remove 1 electron, you need 2.18 into 10 to the power minus 18 joule. To remove 1 mole, we will multiply it with the Avogadro constant, which is 6.022 into 10 to the power 23 atoms per mole. I guess this part is clear to you. Okay. That gives you your ionization enthalpy as 1.31 into 10 to the power 6 joule per mole. So I guess all of you are attending the class. So I would request to just say that if it is clear or not. If you have a doubt, you can ask it. Okay. So this is your correct answer. Now moving on to the next question. Among the second period elements, the actual ionization enthalpy are in the order lithium, boron, beryllium, carbon, oxygen, nitrogen, fluorine and neon. Now you can clearly see an anomaly here, and this is seen for the beryllium. So beryllium is having a higher ionization energy than boron, and your oxygen is having a lower ionization energy than nitrogen. So what is the reason behind it? Just think about it. Okay. So you have some time to solve this question. So what we have done in the previous question, since we have calculated it for 1 electron, but we need it for the 1 mole of that electron. Therefore, we have multiplied the 1 electron term with Avogadro constant. Okay. Now just try to look for the anomaly and try to explain it. Okay, your time is up. If you know the answer, you can just write it by yourself. So, first of all, we will look on to the first anomaly, that why your beryllium has higher delta IH than the boron. Now, we have already talked about it, and I have said a very clear point there, that the reason is the penetration effect and not the full-filled s orbital. Remember this point, this is very, very important. So, if you go back to the structure of atom, what was the reason that your full-filled s orbital was, full-filled d orbital was more stable? The reason was that it is able to exchange its position. As a result, it is able to release the exchange energy, right? So that was the reason for your stabilization of half-filled d orbital. The diagram is clearly given in the NCERT. Now, if you take the case of s orbital, your both electrons have no position to exchange its position. Okay, have no place to exchange its position. One is in the up spin, one is in the down spin. They both cannot interchange their position because their spin is opposite and no other electron is present in that same energy level. Therefore, their stability is not increased due to the half-filled or full-filled case. So this is very important point. Remember this part. Now, if this is clear, what is the reason behind it? The reason is your penetration effect. So your s electrons are more penetrated, or you would say they are more closer to the nucleus. Then comes your p, then comes your d, and lastly your f. Now coming on to the two elements whose configuration we have to consider. I guess this part is clear to you, right? About the exchange energy. So this is very, very important to consider. So the reason behind it is that the beryllium removes a 2s electron. Okay, beryllium removes a 2s electron, whereas boron removes a 2p electron. Now, since your 2s electron is penetrated, now what is the sense of penetration? Means it is more closer to the nucleus. Now, if it is more closer to the nucleus, that means the electrostatic force of attraction is high. Therefore, it is difficult to remove the electron. In the case of what? In the case of beryllium as compared to the boron. And therefore, the first anomaly is explained. Now, moving on to the second anomaly. Now, here you can give the reason of half-filled subshell, because your p electron has a position to exchange its position and give out the exchange energy and hence stabilize it. So, let us move on to that. So, here the reason would be the half-filled subshell. So, remember this half-filled is only applicable to p and higher subshell, not to the s. So oxygen has a lower ionization enthalpy than nitrogen, although oxygen comes after nitrogen. You can see the periodic table for that. But due to the half-filled p subshell, which is specifically 2p subshell of the nitrogen, it is more stabilized and hence we require more energy to take out the electron from the nitrogen atom as compared to the oxygen atom. I guess these two anomalies are clear to you in terms of the fundamentals. So this is very, very important to understand that what is the difference between these two. Okay. Now if this is clear, let us move to the next question. Here is your next question. Which of the following pairs of elements would have more negative electron gain enthalpy? Now again, this is a tricky one. We have already discussed about this anomaly. Oxygen or fluorine, fluorine or chlorine. Your time to solve this question starts now. Now, if I look at the first question, what would be the answer? It would be fluorine. For the second one, it would be chlorine. What is the reason behind it? Let us talk about it. So I will deal only with the anomaly, which is the second case. So that is more important here, because we know that as we move from left to right across a period, your electron gain enthalpy becomes more and more negative. Okay, and that is true for the oxygen and fluorine. But what about the fluorine and chlorine? We have seen that already. That is, second period elements are very compact in size, and as a result, it results in a very high electronic repulsion. Now, this is seen for the oxygens and sulfur case, whereas for fluorine and chlorine case, both means sulfur has more negative electron gain enthalpy than oxygen, and same is the case for chlorine, which is here. What is the reason behind it? The reason is the small size. So as soon as you add electron to a small sized atom, it faces a lot of electronic repulsion, and therefore it is difficult for the atom to take up that electron. As a result, the electron gain enthalpy is less negative than the expected one. Now, this makes clear that the electron gain enthalpy of oxygen is less negative than the sulfur, which is opposite of the given trend or the trend that we know. Similarly, for fluorine, it is less negative than the chlorine. I guess this is clear to all of you. Now, moving on to the next question. Would you expect the second electron gain enthalpy of OS positive, more negative, or less negative than the first? Justify your answer. So you have some time to solve this question. Your time starts now. You already know that the first electron gain enthalpy for every element, like your oxygen and all, is almost negative in the S and P block, except your noble gas. But the second electron gain enthalpy is still a question for you. So let us see how we can solve it. So first of all, when an electron is added to the oxygen atom, the energy is released, as I have talked about it. Therefore, it will be negative. This is for the first electron gain enthalpy. This can be seen in this equation also. Now, what about the second one? So, this is the tricky part. Although you are adding an electron to an already negative charge species, but since you are giving oxygen a stable electronic configuration, right, which is a complete octet one. Therefore, the second electron gain enthalpy of oxygen is positive. Okay. So two things are there. So I have told it opposite. So first one is negative. No problem in that. It is easily accepting the electron. Therefore, it is releasing energy. But in the second case, although it is gaining the stable electronic configuration, but since you are adding it to a negatively charged species, therefore it will require energy to do this process. Okay, I guess it is clear to you. Sorry for the previous confusion. So you are adding an electron to the negative species, therefore it will be positive. You have to supply energy to do this second electron gain enthalpy process. Okay, now this is the last question for today's class. Considering the elements beryllium, aluminium, magnesium and potassium, the correct order of their metallic character is. Remember students, we have already talked about how the metallic character varies. So there are 4 series given. Your time starts now. So what will be the correct answer? I guess it's a very simple one to solve. So your time is up. The correct answer will be option number D. Potassium, then magnesium, then aluminium and then boron. So in this question you have to consider 2 things. First of all, we know that on moving right to left across a period, the metallic character, what happens? It increases. Okay, the metallic character decreases as we move from right to left. We know it, and as a result, it is more metallic. The group 1 and group 2 are more metallic. What about the down the group? So metallic character increases as you move down the group. So here From left to right, the metallic character decreases, and moving down the group, the metallic character increases. And hence, the potassium will be the most metallic one, and the boron will be the least metallic one. And this will give you your correct answer. So in this you will write metallic character decreases, and in down the group you will write increases. So this was all from the question part. Now we will see on to the DPPs. Just wait for a while I switch to the DPPs. So here is the first question. Which of the following incorrectly describes the oxidation state? Correctly describes the oxidation state of oxygen in OF2 and Na2O. So this is a very simple one. What will be the correct answer for this? You have to simply look for the oxidation state of oxygen in OF2 and NO2O. So since your fluorine is more electronegative, it will have oxidation state of -1. Now there are 2 fluorines, therefore this will have a total of -2. Okay. Now to keep this thing positive, oxygen will have oxidation state of +2. Now you don't need to go for the second one. It is clear from the first one only that your correct answer will be A. Now moving on to the next question. The formula for the compound between the aluminium and sulfur is, you just have to look for the valency of aluminium and sulfur. So aluminium has a valency of 3 and sulfur has a valency of 2. Therefore, the correct answer will be Al2S3. Next, which of the following statements about the anomalous behavior of the second period element is incorrect? They exhibit high electronegativity than the subsequent group members. They can form p-pi bond, multiple bonds. Their covalency is 6 due to available d orbitals, and they show diagonal relationship with the elements of the next group. So which is the incorrect one? Incorrect one. You have to look for the incorrect one and not the correct one. So this is important to note here. So this is obviously correct. Your option number D, that they do show the diagonal relationship. Okay. They have a higher electronegativity than the other because electronegativity decreases down the group. But this is incorrect. You look for any second period, you won't see the d orbital. So you don't have it for the nitrogen. Okay, you don't have it for the oxygen, neither for the fluorine. They don't have the d orbital. Therefore, the correct will be, I would say the incorrect statement would be C. I guess it is clear to you. Moving on to the next question. The oxidation number and covalency of aluminium in AlCl H2O whole 5 2 plus are respectively. So this is a good one. If you are not able to solve one, no problem. So you will be able to solve one when you will meet the chapter coordination compound. Still, if you know the answer, you can just write it in the chat section. Okay, let us see. So first of all, we don't know that what is the oxidation number of aluminium. So let us take it as X. Chlorine here will obviously will be in the -1 oxidation state. H2O is neutral, we know it. Water is neutral, so it will be 0. Now overall charge is 2 positive. So I am just giving you an algorithm to solve it. If you will solve it, you will get it +3. Okay, so this is +3 for 2 options, A and C. Now what about the covalency? This is the important one. So 6 atoms are bonded to the aluminium, 1 chloride atom and 5 water molecules. Therefore, your correct answer will be A, that your covalency will be 6. So +3 and +6 will be your correct answer. Moving on to the next question. Which of the following pairs of element demonstrates a diagonal relationship in the periodic table? Lithium, sodium, beryllium, aluminium, boron and carbon, fluorine and chlorine. So what will be the correct answer? If you look at the periodic table, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. Then here you will write sodium, magnesium, aluminium, then silicon, phosphorus, sulfur, chlorine, argon. Lithium and magnesium have a diagonal relationship, then your beryllium and aluminium, boron and silicon, and so on. So lithium and sodium is totally incorrect. Fluorine and chlorine is also not correct. Okay. So this diagonal relationship is not true for these elements, right? Similarly, boron and carbon is still incorrect. The correct answer will be option number B, beryllium and aluminium. Okay, so this was all for today's lecture. In few minutes, our maths faculty will join you. Just wait for a while.